Hi, Steve Hughes here, and in this video I want to show you some practical ways of demonstrating the strong nuclear force in the classroom. Before we get into that, I just want to put the strong force into context. Now, in order of familiarity, the four fundamental forces of nature are gravity, the electromagnetic force, the weak nuclear force, and the strong nuclear force. Now, we're all familiar with gravity. It makes things fall down to the ground. What goes up must come down. It keeps the moon in orbit around the Earth and the planets in orbit around the sun. The electric force, again, very familiar with that. Electric lights, computers, phones, electric vehicles, and even the nerves in our body are electrical signals, or they pass electrical signals. Okay, now let's just get on to why there has to be a strong nuclear force. Now here I've got a model of an atom, the simplest atom, which is a hydrogen atom, where we've got a proton and we've got an electron. This is totally out of scale, and something else. Subatomic particles don't have colour, they can't. For example, a proton is 1 billion times smaller than the wavelengths of light. So they can't have colour as we understand it. Now, so we've got a proton with the electron going around it, and it's the electrical attraction between the proton and the electron which keeps the electron in orbit. There's the sort of planet or solar system model of the atom, which I think is quite good for this. And so in the same way that gravity keeps a planet in its orbit around the sun, so the electrical attraction between a proton and an electron, or protons if it's more than helium, that attraction keeps the electrons kind of in orbit around the centre of the atom, around the nucleus. Now the problem is, in the nucleus, for elements which are of higher atomic number than hydrogen, helium, lithium, etc., then there's more than one proton in the nucleus. So the question is, what holds those protons in the nucleus? What can counterbalance the enormous electrostatic repulsion? And it's the strong nuclear force, as its name implies. It's strong. In fact, ballpark figure is about 100 times stronger than the electric force. So that can hold the protons in the nucleus and also hold the neutrons in the nucleus. Although the neutrons are neutrally charged, hence their name, there's nothing kind of to stop them just wandering out from the nucleus if they were there and there was no extra force holding them in. Now, the scale of the strong nuclear force and also the weak nuclear force is very, very small. It's right down at the scale of the nucleus, hence the name, nuclear force. Now, to try and understand just how small a proton is, 10 to the minus 15 of a metre, here I've got a metre rule, which is divided up into 1,000 millimetres. Now, if you imagine one of those millimetres expanded, so it's a metre, and then we divide by 1,000 again, so we've got 1/1000th of a metre, or 1,000th of a millimetre, 1/1000th of a metre, that's a micrometre. Then we go down another factor of 1,000, and we get a nanometre, as in nanotechnology, and it's about the scale of viruses. And 10 times smaller than that, it's about the size of a hydrogen atom. Then from a nanometre, divide by another 1,000, and we get 1/1000th of a metre, and then we've got to go 1,000 times again, and we get to a quadrillionth of a metre, or 10 to the minus 15. And that's got a special name in nuclear physics, and that's a femtometre. So a femtometre is 10 to the minus 15 of a metre, which is about the size of a proton and a neutron. In fact, those two particles, protons and neutrons, are collectively known as nucleons. So when I use the term nucleon, that's either a proton or a neutron. So here we've got two boards representing nucleons, so that could be 2 protons, two neutrons, or a neutron and a proton, or vice versa. Now, out of about, if say that's 3 femtometers, so 3 times 10 to the minus 15 meters, so very, very small. So out there, basically, the strong nuclear force is 0. There's no attraction or repulsion. But then when we get into about 2, it kind of kicks in and the 2 nucleons get attracted together. We get maximum attraction about just over 1 femtometer, and then it drops off to 0, then just under a femtometer, about 0.8. That's when there's no more attraction, and if the nucleons get closer together, we then get repulsion. In view of the very short range of the strong nuclear force, essentially it's a contact force. So one practical example actually is Velcro. So Velcro, even very close, there's no force there. You've got to actually physically touch the pieces together, and then we get contact. So that's one way of explaining the very short-range nature of the strong nuclear force. So another analogy is a magnet. Here I've got a balled rubber, sort of magnetic, and notice, you can see there on the video, that I've got to get quite close to the board for the actual magnetic force to kick in. And at home you could do this with a fridge magnet. You've got to get, in fact they're quite good because they're very powerful, you've got to get quite close to a fridge before the magnet actually kicks in. So that's another analogy to the short range. And also we've got attraction there, and if I sort of push on there, that's like where we're actually sort of pushing the nucleons together, and if we've got a flexible screen, it'll push back. So here I've got a Perspex cylinder with 2 very strong rare earth magnets. You have to be careful with these. I've smashed them before where they've come together, and also I've given myself a blood blister where my finger's been caught between the 2 magnets, so you do have to be careful. So I've got them in here, and the force of gravity, that represents the attraction of the force, and then the magnetic force represents the repulsion. So these 2 poles here are opposing either 2 north poles or 2 south poles. And you'll see that what happens that if we just leave it, then there's a kind of a rest position here where the magnet sits at a certain position. So that's like where the nucleons are at about 0.8 femtometers apart. That's that point where they like to sit, where it's between attraction and repulsion. So you may have wondered why this diagram was behind me during the previous videos. This shows a plot of the nuclear strong force. It's one possible model from the Reid potential. I'll put a link to the paper that this is in the description, video description. But here we've got a nucleon here, and you can see it's basically about 3 femtometers. We've got very, very small attraction, but then as the nucleons get closer, there's another nucleon sort of over here somewhere. So as we get closer, we've got the attraction, we've got sort of maximum attraction down here, and then it reduces off. So it's still attraction here, it's just less, the attraction is getting less. Then it reaches 0, so that's that midpoint between attraction and repulsion, and then beyond that we've got repulsion. So if nucleons do get crushed together, they actually get pushed in, and energy gets stored in the strong nuclear force, and that can make things bounce away. So for example, in a type 2 supernova explosion, an iron core collapses and the iron gets split up into nucleons, protons and neutrons, and they all come together like this, and so we get something called core bounce, where the nucleons actually bounce off each other, mostly neutrons, because the core turns into a neutron star in many cases, and neutron stars are called neutron stars because they are mostly neutrons. They do have protons as well. So that happens there. So when we go from the force plot and we integrate it, we get the potential plot like this, and that gives the amount of energy that can be released when a nucleon comes towards another one. It starts at 0, that may seem a bit strange, but often potential energy starts at 0 and then it goes down. It becomes less because it's negative. And so here we come down and we go to a minimum there. So if our nucleon is here and we could somehow hold it and release it, then there'd be still no energy to be released. And here, energy's got to be put in to push the nucleons together. So when we differentiate the force function, we get this function here. It's a kind of an acceleration of the force function, and we've got the corresponding points here. So you see there's a peak there, and that corresponds to the steepest point of that curve. It's called an inflection in calculus. And then down here where we've got the maximum attraction, and that's a flat bit of curve, so the gradient is 0, and we can see appropriately it's reached 0 there. So this is a nice way of showing integration and differentiation in a kind of a circuit all based on the strong nuclear potential.